Hi guys, once again this is Engineer Duman Arabis, and uh, this day I will be solving a problem. This is an example of a topic in statics, no? um, Equilibrium of non-concurrent force system. Okay, so without any further ado, let's start. So here's the problem. The beam ABC is hinged at wall A and supported by a cable at C. Carries a distributed load over part of its length, no, from A to B, no, as shown in the figure. The weight of the beam is 80 pound per feet. Okay, so first question, determine the tension in the cable. Second question, determine the reaction at A. Okay, so let's first interpret the problem. So as we can see, uh, the force system is composed of a member ABC, and it is supported by a hinge at A, and at the point C supported by a cable. Okay, so let's start with free body diagram. Okay, so we isolate the beam, and because point A is a hinge connection, so we have two reactions, the vertical and horizontal reaction, RAY and RAX, and at point C there's a tensile force. Okay, and again for cable, it is always away, no, the force acting on the cable. So as we can see, the direction of force T is away from the point of connection. Okay, so the applied forces or loads, we have the applied load 1,200 pound per foot, and we have also the weight of the beam, which is 80 pound per foot. Okay, so okay, so we will apply the equations of static equilibrium. We will first use the summation of moment at A. Okay, so by applying summation of moment at A, the forces that can create a moment about point A are this the weight of the beam, the distributed applied load, and the tensile force. Okay, so we will first resolve this T, or this tensile force, into components. Kana that this one, and okay, this is Ty and this is Tx. Okay, so summation of moment at about point A is equal to 0. We have first the forces that create a clockwise moment. This the weight of the beam and the applied distributed load, and this Tx, since this force, the line of action of this force intersects with point A, so the moment of this Tx is equal to 0. So Ty is a counterclockwise moment, so negative. So Ty is T sine of angle, okay, times the moment arm. This to 1200 times 3, since this distributed load is from point A to point B, which is 3 feet, okay, and 80 times 8, this is the total load or total weight of the beam. 80 times 8, since the length of the beam is 8 feet, so okay, and we can get the magnitude of T, so that value, no? Okay, and to solve the magnitude of the reaction at A, we just simply apply the other two equations of static equilibrium. The summation of forces vertical and the summation of forces horizontal is equal to 0. Oh, using first the summation of forces vertical is equal to 0, so we have Rey, vertical force, positive, no? Positive. And we have Ty, T sine theta, it is also positive, since the direction of this force is upward. We have 1200 times 3, this force, negative, because it is directed downward, and 80 times 8 downward, still negative, and we get the magnitude of Rey. And the same way, we will apply summation of forces horizontal. We can get Rax, and to solve the total reaction at A, we use the Pythagorean theorem, and finally we get Ra. Okay, thank you. Babush.